What if everything you see should have never existed at all? Not the stars above you, not the planet beneath your feet, not even the atoms inside your body. According to our best understanding of physics, the universe should have destroyed itself almost instantly after it began. And yet here you are. You are sitting inside a universe that appears stable, structured, and filled with matter. But beneath that calm surface lies a contradiction so profound that scientists are still struggling to explain it. Because in the very first moments after the Big Bang, something impossible happened. Or rather, something that should not have happened did not happen. To understand why, you have to imagine the universe at its very beginning. Not as a vast space filled with galaxies, but as something far smaller, hotter, and more violent than anything we can easily picture. A state where energy and matter were not yet separated in the way we experience them today. A state where particles and their mirror opposites were being created constantly in pairs. Every particle of matter came with a twin, an equal and opposite counterpart, known as antimatter. If a particle is like a tiny piece of substance, antimatter is its reflection in a perfect mirror. Same mass, same properties, but opposite charge. And when matter and antimatter meet, they do not simply bounce off each other. They annihilate completely, turning back into pure energy in an instant. Now imagine a universe where every single particle of matter is paired with an equal amount of antimatter. At first, this sounds balanced, even elegant. But there is a problem hidden inside that symmetry. Because if matter and antimatter were created in exactly equal amounts, then they should have collided and destroyed each other completely, leaving behind nothing but radiation. No atoms, no stars, no galaxies, no life. Just an expanding sea of energy slowly cooling into emptiness. According to the simplest versions of our physical laws, this is exactly what should have happened. In fact, physicists at institutions like CERN have spent decades studying particle interactions under controlled conditions, and what they find reinforces this expectation. Matter and antimatter behave almost identically. They appear to follow the same rules. They should cancel each other out perfectly, and yet when we look out into the universe, that is not what we see. According to observations from NASA and ESA, the observable universe is overwhelmingly made of matter. Galaxies are built from matter. Stars burn using matter. Planets form from matter. Even the most distant regions of space show no large pockets of antimatter. If antimatter galaxies existed in large numbers, we would see unmistakable signatures where they collide with matter galaxies. Bright flashes of high-energy radiation that cannot be explained any other way, but we do not see them. Instead, everything we observe suggests that antimatter is almost entirely absent on cosmic scales, which leads to a question that feels almost uncomfortable to ask. Where did it go? Or more precisely, why was there more matter than antimatter to begin with? Because if even a tiny imbalance existed at the start, even one extra particle of matter for every billion pairs, that tiny difference would be enough to change everything. After all the annihilations finished, that leftover matter would remain, and over billions of years it would become everything you see today. Every star, every galaxy, every living being, including you. According to a study published in Nature, the imbalance needed to explain our existence is incredibly small, almost unimaginably small, roughly one extra matter particle for every billion matter-antimatter pairs, and yet that tiny excess is the reason anything exists at all. If the balance had been perfect, the universe would be empty. If the imbalance had been larger, the universe might have collapsed into something entirely different. What we observe today sits on a razor's edge between existence and nothingness, and the strange part is, we do not fully understand why that edge exists. The laws of physics, as we currently know them, do not naturally produce such an imbalance at the scale we observe. They allow for small asymmetries, but not enough to explain the universe as it is, which means that somewhere in the earliest moments of cosmic history, something subtle shifted, something broke the symmetry, something tipped the balance, and that shift was enough to allow reality itself to survive. When scientists analyze data from observatories like the Hubble Space Telescope or the James Webb Space Telescope, they are not just studying distant galaxies. They are looking back in time, trying to trace the universe to its earliest conditions, trying to understand how such a precise imbalance could emerge from what should have been perfect symmetry. But every answer seems to open another question. Because if the universe is governed by laws, why would those laws allow such an exception? And if it was not the laws themselves, then what caused the deviation? Was it a random fluctuation, a deeper rule we have not yet discovered? or something even more fundamental that we do not yet have the tools to detect. You might expect that after decades of research, this mystery would be close to being solved. But in many ways, it is becoming more puzzling. The more precisely we measure the universe, the more clearly we see the imbalance, and the more we realize that our current theories are incomplete. It is as if the universe is quietly telling us that something is missing, something important, something that lies just beyond our current understanding, and that realization leads to a deeper, more unsettling thought. If the universe should not exist in the way we observe it, then perhaps our understanding of reality itself is not as complete as we believe. Perhaps the laws we rely on are only part of a larger picture, a picture that includes mechanisms we have not yet uncovered, mechanisms that determined whether anything would exist at all, and if that is true, then the story of the universe is not just about stars and galaxies. It is about a fragile imbalance, a tiny difference that made everything possible, a difference that should not have been there, and yet somehow is, which raises the next question. If matter and antimatter were meant to be equal, what exactly broke that balance in the first place? If the universe began in perfect balance, why is there anything at all? This is not just a philosophical question. It is a measurable, testable, deeply scientific mystery that has occupied some of the most advanced laboratories on Earth. Because when physicists describe the early universe, they are not guessing. They are reconstructing it using equations that have been tested repeatedly in particle accelerators and astrophysical observations, and in precise experiments conducted by organizations like CERN and research groups at MIT and Caltech. And those equations tell a very specific story. In the first fraction of a second after the Big Bang, the universe was so hot and dense that energy could transform directly into particles. Not just matter, but equal pairs of matter and antimatter. This is not speculation. It is something we can recreate today. In high-energy collisions inside particle accelerators, scientists routinely observe energy turning into particle-antiparticle pairs, an electron and a positron, a quark and an antiquark, always in pairs, always balanced, and just as consistently when those pairs meet again, they annihilate, returning to pure energy. This process is so fundamental that it is built into the equations of quantum field theory, the same equations that successfully predict the behavior of particles with astonishing precision. So if the early universe followed these same rules, and there is no reason to believe it did not, then it should have produced matter and antimatter in equal amount. And that leads to the central mystery, because equal amounts should mean total destruction. Yet something interrupted that outcome. Something introduced an imbalance so small it almost escapes detection, and yet so powerful it shaped the entire cosmos. To understand how strange this is, imagine watching a perfectly balanced system, a scale with equal weights on both sides. You would expect it to remain level. Now imagine that after a brief moment one side suddenly begins to tip, not dramatically, just slightly, but enough that over time the difference becomes overwhelming. The question is not just why it tipped, but what caused the first deviation at all. Because in physics, symmetry is not just an aesthetic idea, it is a guiding principle. Many of the most successful theories are built on the assumption that the laws of nature treat certain things equally, left and right, positive and negative, matter and antimatter. This concept is known as symmetry, and for a long time, scientists believed that the universe respected these symmetries perfectly, especially at its beginning. In fact, early models of the universe assumed that matter and antimatter were created in identical amounts, obeying identical laws with no preference for one over the other. This idea was not just elegant, it was supported by experimental evidence. When physicists at Harvard University and other institutions studied particle interactions, they found that most processes treated matter and antimatter almost identically, so the expectation was clear. The universe should have remained balanced. But when we look at reality, that expectation collapses, because everything we observe is made of matter. From the smallest atoms to the largest galaxy clusters observed by the Hubble Space Telescope, the pattern is the same. Matter dominates. Antimatter is almost nowhere to be found. And that absence is not just a curiosity, it is a clue that something in the early universe broke the symmetry, but not in a dramatic or obvious way. Instead, the break must have been incredibly subtle, so subtle that it only revealed itself after billions of annihilations had already taken place. According to research published in journals like the Astrophysical Journal, The imbalance required to produce the observable universe is astonishingly small, roughly one extra matter particle for every billion matter-antimatter pairs. Think about that. Out of 1 billion pairs that cancel each other out completely, leaving nothing behind, one particle survives. Just one. And that single survivor becomes part of everything. Scale that up across the entire universe and you begin to see how galaxies form, how stars ignite, how planets emerge, how life becomes possible. All from a difference so small it feels almost accidental. But this raises an even deeper question. Was it accidental? Or was it the result of a hidden rule? Because in physics, tiny effects usually have underlying causes. They are not random in the way we might imagine. They emerge from deeper structures, deeper laws. And if such a law exists for this imbalance, we have not fully identified it yet. One of the most intriguing aspects of this mystery is that it connects the smallest scales to the largest. Particle physics and cosmology become inseparable here. The behavior of subatomic particles in the first moments after the Big Bang determines the structure of the entire universe billions of years later. This is why experiments conducted at facilities like CERN are so important. By studying how particles behave under extreme conditions, scientists hope to uncover the mechanisms that could have created the imbalance. But so far, the answers remain incomplete. We have hints, we have partial explanation. We have observed small violations of symmetry in certain particle interactions, but none of them fully account for the scale of the imbalance we observe. It is like finding a small crack in a wall and realizing that it cannot explain why the entire structure is leaning. There must be something deeper, something more fundamental, and that realization leads to a shift in perspective, because instead of asking why the universe exists, we begin to ask a more precise question. Why does matter exist in excess? Why did the universe choose matter over antimatter? Or perhaps more accurately, what process in the early universe created that preference? This is the mystery that drives modern physics. It is not just about understanding the past. It is about uncovering the rules that govern reality itself. Because if we can explain why matter dominates, we might uncover new physics, new principles that extend beyond our current theories, principles that could reshape our understanding of everything from the smallest particles to the largest cosmic structures. And as we begin to explore those possibilities, we are forced to confront an uncomfortable truth. The universe we observe may not be the most natural outcome of its own laws. It may be the result of a rare imbalance, a slight deviation, a moment where perfect symmetry failed, and that failure made everything possible, which brings us to the next step in this story. Because before we can understand what went wrong, we have to understand what scientists originally believed would happen, and why that belief seems so certain. For a long time, scientists believed the universe began in perfect balance, not just balanced in a general sense, but governed by deep symmetries that dictated how everything should behave. These symmetries were not guesses. They emerged naturally from the mathematical frameworks that describe reality at its most fundamental level, frameworks that had been tested repeatedly in experiments and had proven to be remarkably accurate. In fact, much of modern physics is built on the idea that symmetry is not just common in nature, but essential. It shapes the laws themselves. It determines how particles interact. It defines what is possible and what is forbidden. One of the most important of these symmetries is known as charge symmetry. The idea that if you take a particle and flip its electric charge, turning matter into antimatter, the laws of physics should remain unchanged. An electron and a positron should behave in exactly the same way except for their opposite charges. This principle extends further into what physicists call CPT symmetry, a combination of three transformations: charge which swaps matter with antimatter, parity which flips spatial coordinates like looking in a mirror, and time which reverses the direction of time itself. According to the standard model of particle physics, CPT, symmetry must always be conserved. It's one of the most fundamental assumptions built into the theory, and so far every experiment has confirmed it, which means that at the deepest level the universe treats matter and antimatter as equal, perfectly equal, at least in principle. This idea was not just theoretical, it was supported by experimental evidence gathered over decades. When scientists created antimatter in laboratories, they observed that it mirrored matter almost exactly. The same lifetime, the same interactions. According to experiments conducted at CERN, when particles and antiparticles are produced under controlled conditions, they follow the same physical laws with extraordinary precision. Any differences are incredibly small, often so small that they are difficult to measure. This reinforced the belief that the early universe must have been perfectly symmetric. When energy condensed into particles, it should have produced equal amounts of matter and antimatter. No preference, no imbalance, just perfect balance. And if that balance existed, the outcome seemed inevitable. Matter and antimatter would meet. They would annihilate, and the universe would be left with nothing but radiation. This prediction was not seen as a flaw. It was seen as a natural consequence of elegant and well-tested principles. In fact, many physicists found it satisfying. The idea that the universe could emerge from symmetry and then return to simplicity. A brief moment of complexity followed by a return to pure energy. But there was a problem, because when we looked at the universe, it did not match that prediction. Instead of emptiness, we saw structure. Instead of symmetry, we saw imbalance. Instead of annihilation, we saw survival. And that forced scientists to reconsider their assumptions. But before that shift happened, the belief in perfect symmetry was so strong that it shaped entire generations of research. It influenced how physicists thought about the early universe. It guided the development of theories. It defined what was considered possible. To understand why this belief was so compelling, you have to consider how successful symmetry has been in physics. Many of the most powerful theories we have are based on symmetrical principles, the laws of electromagnetism, the conservation of energy, the behavior of fundamental forces. All of these rely on symmetries that have been confirmed through observation and experiment. Even the discovery of new particles has often been guided by symmetry. Physicists predicted their existence based on mathematical consistency, and later experiments confirmed those predictions. This pattern reinforced the idea that symmetry is not just a feature of the universe, it is a guiding rule, a principle that underlies everything. So when early cosmological models were developed, it was natural to assume that the universe began in a perfectly symmetric state. According to these models, the Big Bang produced a hot, dense environment where particles and antiparticles formed in equal numbers. They interacted, collided, and annihilated, and over time the universe cooled and expanded, leaving behind a uniform background of radiation. This picture was consistent with many observations. For example, the cosmic microwave background radiation detected and later studied in detail by missions like Planck Space Observatory shows that the early universe was incredibly uniform, almost perfectly smooth. This uniformity seemed to support the idea of an initial symmetric state, a universe that began in balance and evolved according to simple, elegant laws. But there was a subtle contradiction hidden within this picture, because while the background radiation is uniform, the matter distribution is not. Galaxies, stars, and planets exist. Structures are formed, and those structures require matter, not radiation, which means that at some point the assumption of perfect symmetry must have broken down. But in the early days of cosmology, this contradiction was not immediately clear. It took time, improved observations, and more precise measurements to reveal the full extent of the problem. As telescopes became more powerful and data more detailed, scientists began to notice that the universe was not just slightly imbalanced, it was overwhelmingly dominated by matter. And that dominance could not be explained by the models based on perfect symmetry. This realization marked a turning point, because it meant that one of the most trusted principles in physics might not apply in the way we expected, or at least not in the early universe. It forced scientists to ask a new question. If symmetry is so fundamental, why did it fail here? Why did the universe not follow the simplest possible path? Why did it not return to pure energy after the Big Bang? Instead of eliminating matter and antimatter equally, something allowed a tiny fraction of matter to survive, and that survival changed everything. What makes this even more intriguing is that the laws of physics themselves seem to allow for small violations of symmetry under certain conditions, not large enough to be obvious, but enough to introduce slight differences in behavior, differences that could over time lead to significant consequences. These small asymmetries were not part of the original assumptions. They were discovered later through careful experimentation and observation, and they hinted at a deeper layer of complexity beneath the apparent simplicity of symmetry, a layer where the rules are not perfectly balanced, where slight preferences can emerge, where the universe can deviate from its expected paths. But even with these hints, the core belief remained, that any asymmetry would be small, insufficient to explain the vast imbalance we observe today, and so the mystery deepened because now we had two conflicting ideas. On one hand, the universe should have been symmetric. On the other hand, it clearly is not, and the gap between those two ideas became one of the most important problems in modern physics, a problem that continues to challenge our understanding, a problem that suggests we may be missing something fundamental, something that connects the earliest moments of the universe to everything we see today. And as scientists began to confront this contradiction more directly, they started to uncover evidence that the problem was even more serious than it first appeared. Because it was not just that the universe was imbalanced, it was that the known laws of physics could not fully explain why, which leads us to the next stage of the story, the moment when the contradiction could no longer be ignored and when the problem of the missing antimatter became impossible to dismiss. At first, the imbalance did not seem like a crisis. It looked like a small inconsistency, something that might be explained with better data, or a minor adjustment to existing theories. But as observations improved, that hope began to fade, because the more precisely scientists measured the universe, the more obvious the contradiction became. This was not a small deviation from expectation. It was a fundamental mismatch between theory and reality. The universe was not just slightly dominated by matter, it was overwhelmingly so, and that dominance could not be explained by the laws of physics as they were understood. One of the clearest pieces of evidence came from observations of high-energy radiation. If large regions of antimatter existed somewhere in the universe, they would inevitably come into contact with matter at the boundaries, and when they did, the annihilation would produce intense bursts of gamma rays. These signals would be unmistakable, bright, energetic, and impossible to confuse with ordinary astrophysical processes. Scientists have searched for these signatures using instruments developed by NASA and ESSA, scanning the sky for evidence of matter-antimatter collisions on cosmic scales, but they have not found them, not at the level that would suggest entire galaxies made of antimatter. Instead, the data shows a universe that is almost entirely composed of matter. This absence is not just surprising, it's deeply troubling from a theoretical perspective, because it means that the symmetry we expected at the beginning did not survive. And whatever broke that symmetry did so in a way that affected the entire observable universe. Another line of evidence comes from the cosmic microwave background, the faint afterglow of the Big Bang measured with incredible precision by missions like the Planck Space Observatory. According to data analyzed by scientists at institutions such as Caltech and MIT, the distribution of matter in the early universe was already slightly uneven, not in the sense of large clumps, but in the sense that matter existed at all in a form that could later collapse into structure. If matter and antimatter had annihilated completely, there would be no such seeds for galaxies, no density fluctuations that could grow over time. The fact that we observe these patterns means that matter survived the annihilation phase, and it survived in sufficient quantity to shape the entire cosmic structure. This creates a tension that is difficult to resolve. Because the standard model of particle physics, one of the most successful theories ever developed, does not predict an imbalance of this magnitude. It allows for small differences between matter and antimatter behavior, but not nearly enough to explain the universe we see. This gap between prediction and observation is what physicists refer to as the baryon asymmetry problem, a name that sounds technical but describes something very simple. Why is there more matter than antimatter? Or more precisely, why is there any matter at all? The seriousness of this problem becomes clear when you consider how precisely the standard model has been tested. Experiments at CERN and other facilities have confirmed its predictions to extraordinary accuracy. From the behavior of quarks to the properties of the Higgs boson, the theory works remarkably well, and yet in this one crucial area it falls short. It cannot account for the imbalance that allowed the universe to exist. This is not a minor flaw, it is a signal that something important is missing, something that lies beyond the standard model, and that realization has profound implications because it suggests that our current understanding of physics is incomplete, not in a small way, but in a way that affects the very existence of everything. To make matters even more intriguing, the required imbalance is incredibly specific. Too small and the universe would be empty. Too large and the universe might have evolved in a completely different way, perhaps collapsing too quickly or forming structures too rapidly. The value we observe appears finely tuned, balanced on a narrow range that allows for the formation of galaxies, stars, and life. This has led some scientists to describe the situation as a kind of cosmic coincidence. But in physics, coincidences are often clues. They point toward deeper principles that have not yet been uncovered. And so researchers began to look for mechanisms that could produce the required imbalance. Mechanisms that go beyond the standard model. One of the key insights came from a physicist named Andrei Sakharov. In 1967, he proposed a set of conditions that must be satisfied in order for a matter-antimatter imbalance to arise. These conditions, now known as the Sakharov criteria, provide a framework for understanding how symmetry could be broken in the early universe. According to this framework, three things are necessary. First, there must be processes that violate baryon number, meaning they allow the number of matter particles to change. Second, there must be violations of certain symmetries between matter and antimatter, specifically what is known as CP symmetry. And third, these processes must occur out of thermal equilibrium, meaning the universe must not be in a perfectly balanced state when they happen. These conditions are not arbitrary. They are derived from the fundamental principles of physics, and they provide a roadmap for scientists searching for the origin of the imbalance. But satisfying these conditions in a way that produces the observed asymmetry is extremely challenging. The standard model does include some CP violation, but not enough. It allows for slight differences in how certain particles decay, but the effect is too small to account for the vast dominance of matter. This is where the problem becomes even more fascinating, because it suggests that there must be additional sources of asymmetry, new physics that we have not yet discovered. Possibilities include new particles, new interactions, or entirely new principles that extend beyond our current theories. And this is not just speculation. Experiments are actively searching for these effects, looking for deviations from the standard model, looking for hints of new physics, looking for the missing piece of the puzzle, but so far the answers remain elusive. We see the outcome clearly, a universe filled with matter, but the mechanism that produced it remains hidden, and that gap between what we observe and what we can explain is one of the most compelling mysteries in science, because it touches on the deepest question we can ask. Why does anything exist at all? And as scientists continue to investigate this question, they have begun to turn to new tools, new experiments, new ways of probing the fundamental nature of reality. Because if the answer is not in the theories we already have, then perhaps it lies in the data we have yet to collect. Which brings us to the next phase of this story, the moment when technology allowed us to recreate conditions similar to the early universe, and to begin searching directly for the tiny asymmetries that might explain everything. To understand what went wrong at the beginning of the universe, scientists realized they needed to do something extraordinary. They needed to recreate in some small way the conditions of the Big Bang itself, not the full scale of it, of course. But the energy, the collisions, the environment where particles and antiparticles could emerge and interact. Because if the imbalance between matter and antimatter was real, then traces of it might still be visible in the behavior of particles today. And so over decades, humanity built machines unlike anything that had existed before. Vast underground structures where particles are accelerated to near the speed of light and smashed together with incredible energy. The most powerful of these machines is located beneath the border of France and Switzerland, a facility known as CERN. Inside it lies the Large Hadron Collider, a circular tunnel stretching 27 kilometers where protons are accelerated and collided at energies that briefly recreate conditions similar to those just after the Big Bang. When these collisions occur, energy transforms into matter, particles burst into existence, quarks, leptons, bosons, and crucially their antimatter counterparts, just as the equations predict. In these tiny controlled explosions, scientists can observe how matter and antimatter behave, how they are created, how they decay, how they interact, and most importantly whether there are any differences between them. Because even the smallest asymmetry could hold the key to the largest mystery. According to experiments conducted at CERN, including those from detectors like LHC, B, there are indeed slight differences in how certain particles and antiparticles behave. These differences are known as CP violations. They represent a subtle breaking of the symmetry that was once thought to be perfect. For example, certain particles containing strange or beauty quarks decay at slightly different rates than their antimatter counterparts. The difference is tiny, But it is measurable, and it proves something important. The universe does not treat matter and antimatter as perfectly identical in all situations. There is a preference, a bias, a slight tilt in the rules. At first glance, this might seem like the answer. If matter behaves just a little differently than antimatter, then over time that difference could accumulate, leading to the imbalance we observe today. But there is a problem. The magnitude of these observed violations is far too small. According to studies published in journals like Physical Review Letters, the CP violation measured in known particles cannot account for the scale of the matter dominance in the universe. It's like finding a tiny leak in a dam and realizing it cannot explain why the entire reservoir is drained. The effect is real, but it is not enough. And so the mystery deepens, because now we know that symmetry is not perfect. But we also know that the imperfections we have observed are insufficient. There must be more sources of asymmetry, more processes that occurred in the early universe, processes that we have not yet detected. This realization has driven scientists to expand their search, not just at CERN, but in laboratories around the world, including experiments designed to study neutrinos. Among the most elusive particles in the universe, neutrinos are incredibly light. They rarely interact with matter. Trillions of them pass through your body every second without you noticing. But despite their ghost-like nature, they may hold crucial clues. Experiments such as those conducted by collaborations involving Fermilab and KE have begun to investigate whether neutrinos and antineutrinos behave differently. If they do, it could provide a new source of CP violation, one that might be strong enough to explain the imbalance. Early results are intriguing. Some measurements suggest that neutrinos may indeed violate symmetry in ways that differ from other particles. But the data is still incomplete. The uncertainties are large, and scientists are cautious. Because in physics, extraordinary claims require extraordinary evidence. At the same time, astrophysical observations continue to play a role. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope allow scientists to look deeper into the universe than ever before, not just in space but in time, observing galaxies as they existed billions of years ago, studying how matter clumped together, how structure formed, and how the early universe evolved. These observations provide constraints, limits on how much matter must have existed at different stages, limits that any successful theory must satisfy. So the investigation is happening on multiple fronts. In underground accelerators, in deep space observatories, in theoretical calculations performed by physicists at institutions like Harvard University and Caltech, all searching for the same answer. What created the imbalance? What allowed matter to survive? What broke the symmetry? And what is becoming increasingly clear is that the answer is not simple. It is not a single discovery or a single experiment. It is likely a combination of effects, some of which we have already observed, and other in the years that remain hidden. This is what makes the problem so compelling. It sits at the intersection of theory and observation, of the smallest particles and the largest structures, of what we know and what we have yet to discover. Because every time we build a more powerful accelerator, every time we collect more precise data, we are not just learning about particles, we are learning about the origin of existence itself. And with each new result, the picture becomes slightly clearer, but also more complex. Because the more we uncover, the more we realize how much we do not yet understand, which leads to the next moment in this story. The point where the data stopped being subtle and began to reveal something truly unexpected, something that challenged even the expanded view of symmetry breaking and forced scientists to rethink their assumptions once again. For years, scientists expected that if an answer existed, it would reveal itself slowly. A gradual accumulation of data, small refinements to existing theories, a steady narrowing of possibilities. But instead, what began to emerge from the experiments was something more unsettling. Not a clear solution, but a series of hints that pointed in directions no one had fully anticipated. Because the deeper scientists looked into the behavior of particles, the more they realized that the asymmetry between matter and antimatter was not just present, It was inconsistent. It appeared in some places, vanished in others, and sometimes behaved in ways that did not fit neatly into any existing model. One of the most striking examples came from detailed studies of particles known as mesons. These are short-lived particles that can oscillate between matter and antimatter states. In experiments conducted at CERN and other facilities, scientists observed that certain mesons did not behave identically to their antimatter counterparts. They decayed at slightly different rates. They favored certain pathways over others, and these differences, while small, were undeniable. At first, this seemed like confirmation, evidence that CP violation was real and measurable. But as more data was collected, a new problem emerged. The patterns of violation did not fully align with theoretical predictions. Some measurements were larger than expected, others were smaller, and some hinted at entirely new sources of asymmetry that were not accounted for in the standard model. According to analyses published in journals like Physical Review Letters, these discrepancies, while not yet definitive, suggest that there may be additional forces or particles influencing the behavior of known particles, subtle effects that only become visible under extreme conditions. This is where the story takes an unexpected turn. Because instead of moving closer to a single explanation, scientists found themselves facing a landscape of possibilities, each one plausible, each one incomplete, and each one raising new questions. At the same time, neutrino experiments began producing results that added another layer of complexity. Neutrinos, once thought to be almost irrelevant due to their weak interactions, started to reveal surprising properties. They oscillate between different types as they travel, a phenomenon that was not predicted in the earliest versions of particle physics. And more intriguingly, there are indications that neutrinos and antineutrinos may oscillate differently. If confirmed, this would represent a new form of CP violation, one that could be significantly stronger than what has been observed in other particles. Experiments involving collaborations at Fermilab and KEK have been carefully measuring these effects, sending beams of neutrinos across long distances, detecting how they change over time, comparing the behavior of neutrinos to their antimatter counterparts. The results so far are tantalizing. There are hints of asymmetry, hints that neutrinos may prefer one direction over another. But the data is not yet conclusive, and in science hints are not enough. They must be confirmed with precision, with repeated experiments, with independent verification. Still, the possibility is profound. Because if neutrinos do exhibit strong CP violation, they could be the key to understanding why matter dominates the universe, through a process known as leptogenesis, where asymmetries in leptons like neutrinos eventually lead to an imbalance in baryons, the particles that make up matter. But this is just one possibility. Another unexpected development comes from the study of the early universe itself. Using data from the Planck Space Observatory and other observation, scientists have been able to reconstruct the conditions that existed shortly after the Big Bang. These reconstructions suggest that the universe went through rapid phase transitions, moments where the fundamental properties of fields and particles change dramatically, similar to how water changes from liquid to ice. But on a cosmic scale, some theories propose that during these transitions, conditions could have arisen that temporarily favored matter over antimatter, creating pockets of imbalance that later became the seeds of everything we observe. If this is true, then the asymmetry is not just a property of particles, it is a property of the universe itself, embedded in its evolution, shaped by the way it cooled and expanded. This idea is both exciting and unsettling because it suggests that the laws of physics may not be static. They may have evolved, changed, adapted as the universe unfolded. And if that is the case, then the conditions that created the imbalance may no longer exist, making them difficult to study directly. This is why scientists rely on indirect evidence, on patterns, on subtle signals hidden in data. But interpreting these signals is not straightforward, because different theories can produce similar predictions, and separating them requires precision that is often just beyond our current capabilities. This is where confusion begins to set in. Not confusion in the sense of misunderstanding, but in the sense of complexity, of multiple overlapping explanations, of incomplete information, because every new discovery seems to open more possibilities rather than closing them. And this is a hallmark of deep scientific problems. They do not resolve cleanly. They expand, they reveal layers, They challenge assumptions, and in this case they challenge one of the most fundamental assumptions of all, that the universe is governed by simple, symmetrical laws. Instead, what we are seeing is a universe that may be inherently biased, not in a dramatic way, but in subtle, almost hidden ways that only become apparent when we look closely enough, ways that require enormous effort to detect, and yet those tiny biases are enough to shape everything. This realization changes how we think about the universe. It shifts the focus from perfect symmetry to broken symmetry, from balance to imbalance, from simplicity to complexity, and it raises a new question. If the asymmetry we observe cannot be fully explained by known physics, and if multiple mechanisms may be contributing, then which one is responsible? Or is the answer not a single mechanism at all, but a combination of processes that work together in the earliest moments of existence? This is the puzzle that scientists are now trying to solve. A puzzle with pieces scattered across experiments, observations, and theories. A puzzle that connects the smallest particles to the largest structures. A puzzle that may require entirely new ideas to complete. And as we move forward in this story, we begin to explore those ideas, the competing theories that attempt to explain how the universe tipped the balance, and why that balance never returned. At this point, the mystery becomes harder to ignore. Because we are no longer dealing with a simple gap in knowledge, we are facing a contradiction that sits at the heart of modern physics. On one side, we have a theory that works with extraordinary precision. The Standard Model successfully predicts the behavior of particles in experiments conducted at CERN and laboratories around the world. It explains how forces interact, how particles decay, how the fundamental building blocks of matter behave, and it does so with a level of accuracy that is almost unmatched in science. On the other side, we have the universe itself, a vast observable system filled with galaxies, stars, and matter. A system that clearly does not match the predictions of perfect symmetry, and the gap between these two is not small, it is enormous. Because the Standard Model allows for some asymmetry, but not nearly enough to explain why matter dominates so completely. This creates a kind of tension, a situation where two things that should align do not, and when that happens in physics, it usually means that something important is missing. To understand why this is so difficult to resolve, you have to look at how the Standard Model handles symmetry. It includes a mechanism for CP violation, a way for matter and antimatter to behave slightly differently. This has been observed in experiments involving particles like kaons and B mesons. These results were groundbreaking. They showed that symmetry is not absolute, that there are exceptions. But when scientists calculate how much asymmetry these effects can produce, the answer falls short. By a large margin, according to theoretical estimates, the CP violation in the Standard Model is too weak by several orders of magnitude. It is not even close. This is not a matter of fine-tuning. It is a fundamental limitation, and that limitation forces physicists to look beyond the Standard Model. But stepping beyond it is not easy. Because the Standard Model is so successful, any new theory must not only explain the matter-antimatter imbalance, it must also preserve all the accurate predictions we already rely on. This is like trying to modify a perfectly working machine to fix one problem without breaking everything else. And that is an incredibly delicate task. One of the challenges lies in the nature of the early universe. The conditions under which the imbalance was created are extreme. Temperatures far beyond anything we can directly reproduce, densities and energies that push the limits of our understanding, and processes that occurred in fractions of a second. We cannot go back and observe those moments directly. We can only infer them, reconstruct them from the evidence we have today, and that evidence is incomplete. It's like trying to understand a complex event from a few scattered clues. Each piece tells part of the story, but none of them tell the whole story. This is why the problem feels so confusing, because every time we think we're getting closer, the details become more complicated. For example, the observed CP violation in meson systems suggests that symmetry breaking exists, but its magnitude is too small. Neutrino experiments hint at larger asymmetries, but the data is still uncertain. Cosmological observations provide constraints, but not direct answers, and theoretical models offer possibilities, but often rely on assumptions that have not been verified. All of these pieces exist, but they do not yet fit together into a coherent picture. This is where scientists begin to explore to explore alternative ideas, not just extensions of existing theories, but entirely new frameworks. Some propose the existence of new particles, heavy particles that existed only in the early universe and decayed in ways that favored matter. Others suggest new interactions, forces that are not included in the standard model, but could influence particle behavior under extreme conditions. There are also ideas involving extra dimensions, or modifications to the way time and symmetry are understood. Each of these theories attempts to solve the same problem, but they will approach it from different angles, and each comes with its own challenges, its own predictions, its own uncertainties. What makes this situation particularly difficult is that many of these theories produce effects that are subtle, hard to detect, often requiring experiments that push the limits of current technology, and even when such experiments are possible, interpreting the results is not straightforward, because different theories can produce similar outcomes. It's like trying to identify a distant object through a fog. You can see its outline, you can make guesses about its shape, but you cannot be certain until the fog clears. And in this case, the fog is the limitation of our measurements, the limitation of our instruments, the limitation of our current understanding. Despite these challenges, progress is being made, slowly, carefully, methodically. Each experiment adds a piece to the puzzle, each observation refines our models, each theory pushes the boundaries of what we consider possible. But the central question remains unresolved. Why is there more matter than antimatter? Why did the universe not follow the simplest path? Why did symmetry break in just the right way to allow everything to exist? These are not just technical questions, they are foundational. They touch on the nature of reality itself. Because if the laws of physics cannot fully explain the existence of matter, then those laws are incomplete. And if they are incomplete, then there is more to discover, more to understand, more to uncover about the universe we inhabit. This realization changes the way scientists approach the problem. It shifts the focus from trying to fix small inconsistencies to searching for deeper principles, principles that may redefine our understanding of symmetry, time and the origin of the universe. And as we move forward, we begin to explore all the theories that attempt to do exactly that, the competing explanations that aim to solve the mystery, each offering a different vision of how the universe came to be, and why it did not simply disappear. When a mystery refuses to yield a single clear answer, science does something interesting. It does not stop. It multiplies possibilities. It builds competing explanations, each grounded in real physics, each attempting to solve the same problem from a different angle. And in the case of why the universe exists at all, this has led to some of the most ambitious ideas in modern science. Ideas that stretch from the smallest particles to the earliest moments of time itself. One of the most widely studied explanations is known as baryogenesis, the idea that the imbalance between matter and antimatter was created through processes that directly affected baryons, the particles that make up protons and neutrons. In this framework, the early universe contained interactions that violated baryon number, meaning that the total number of matter particles could change over time. This is not something we observe in everyday conditions, but under the extreme energies of the early universe, it may have been possible. According to theoretical work discussed in journals like Physical Review Letters, certain extensions of the standard model allow for such processes. They introduce new interactions or new particles that can create a small excess of baryons over antibaryons. But there is a challenge. These processes must satisfy the Sakharov conditions. They must break symmetry. They must occur out of equilibrium, and they must do so in a way that produces exactly the right amount of imbalance. Too little and the universe would be empty. Too much and the universe would look very different from what we observe. Another major idea is leptogenesis, a theory that shifts the focus away from baryons and toward leptons, a category of particles that includes electrons and neutrinos. In this scenario, the imbalance begins not with matter directly, but with leptons. Heavy neutrino-like particles in the early universe decay in a way that favors leptons over antileptons. This creates an asymmetry that is later converted into a baryon asymmetry through processes that link the two. This idea is particularly appealing because it connects with what we are observing in neutrino experiments. If neutrinos exhibit strong CP violation, it could support the leptogenesis model. Experiments at Fermilab and KEK are actively searching for these effects, looking for differences in how neutrinos and antineutrinos oscillate, looking for evidence that could confirm this pathway. But again, the data is not yet definitive. It is suggestive, promising, but incomplete. There is also the idea of electroweak baryogenesis, a model that focuses on a specific moment in the early universe when the electroweak force separated into the electromagnetic and weak nuclear forces. This phase transition could have created conditions where symmetry was temporarily broken, allowing for the generation of a matter-antimatter imbalance. In some versions of this theory, bubbles of a new phase form and expand through the universe, and at the boundaries of these bubbles, interactions occur that favor matter over antimatter. This is a vivid image, a universe undergoing a transformation, with tiny regions where the rules are slightly different, regions where imbalance can emerge. But for this mechanism to work, certain conditions must be met. Conditions that depend on the properties of particles like the Higgs boson, and so far measurements of the Higgs at CERN suggest that the standard model alone may not support the required conditions, which means that additional physics may be needed, new particles, new interactions, or modifications to the existing framework. Beyond these more established ideas, there are even more speculative theories. Some propose that the asymmetry is related to physics at extremely high energies, far beyond what we can currently test, possibly connected to grand unified theories, models that attempt to unify all fundamental forces into a single framework. In these scenarios, heavy particles that existed only briefly in the early universe decay in ways that produce an imbalance. These particles would be far too massive to create in current accelerators, which makes direct testing difficult. Others explore the possibility that the asymmetry is linked to the nature of time itself, that the arrow of time, the distinction between past and future, may be connected to the imbalance between matter and antimatter. This idea is still highly speculative, but it highlights how deep the mystery goes. Because we are no longer just asking about particles, we are asking about the structure of reality. There are also ideas involving dark matter, the mysterious substance that makes up most of the mass in the universe. Some theories suggest that the processes that created dark matter may be linked to the processes that created the matter. Antimatter imbalance. If this is true, then solving one mystery could help solve the other. And observations from telescopes like the James Webb Space Telescope and experiments designed to detect dark matter may provide indirect clues. What all of these theories have in common is that they extend beyond what we currently know. They introduce new elements, new assumptions, new possibilities, and that is both their strength and their weakness. Because while they offer potential solutions, they also require evidence. They must be tested, verified, confirmed, and until that happens, they remain possibilities rather than answers. This is the current state of the field, a landscape of competing ideas, each one grounded in real physics, each one attempting to explain why the universe did not annihilate itself, and each one waiting for the data that will confirm or refute it. But even in this uncertainty, there is a progress, because by exploring these theories, scientists are expanding the boundaries of what we understand. They are developing new tools, new experiments, new ways of probing the universe, and in doing so, they are getting closer to the truth. Not in Israel. No, man. But through a process of exploration, of testing, of refining, and as this process continues, certain ideas begin to stand out, not as final answers, but as leading candidates, theories that align more closely with the data, that offer explanations consistent with multiple observations, and that can be tested in the near future. Which brings us to the next stage of the story, the moment where hints begin to solidify, where experiments start to reveal patterns that could point toward a real solution, and where the possibility of a breakthrough becomes more tangible than ever before. For a long time, the search felt like it was circling the answer without ever quite reaching it. Hints appeared, then faded. Measurements improved, but never enough to close the gap. But in recent years, something has started to change. Not a single discovery that solves everything, but a convergence. Different lines of evidence beginning to point in similar directions. Subtle patterns emerging from data collected across completely different experiments. And when independent paths begin to align, scientists pay attention. One of the most important developments has come from increasingly precise measurements of CP violation in particle systems. At CERN, experiments such as LHCb have been studying the behavior of particles containing beauty quarks. These particles are ideal for detecting tiny asymmetries because they decay in complex ways that can reveal hidden differences between matter and antimatter. Over time, these measurements have become more accurate, and while they still fall short of explaining the full imbalance, they have revealed something important. The asymmetry is real, consistent, and deeply embedded in the laws of particle interactions. This reinforces the idea that the imbalance did not arise from a single rare event, but from processes that were built into the fabric of the early universe. Processes that operated repeatedly, amplifying tiny differences over time. At the same time, neutrino experiments are moving closer to a decisive result. Facilities connected to Fermilab and KEK have been refining their measurements of neutrino oscillations, tracking how neutrinos change identity as they travel. Comparing these changes with those of antineutrinos, and what they are finding is increasingly suggestive. Some datasets indicate a preference, a directionality in the way neutrinos behave. If confirmed, this would represent a new and potentially much stronger source of CP violation, one that could finally bridge the gap between theory and observation. It is not confirmed yet, but the possibility is enough to shift the focus of the field, because if neutrinos hold the key, then the solution may lie in a part of physics that was once considered almost invisible, a subtle, elusive sector that quietly shapes the universe in ways we're only beginning to understand. Meanwhile, cosmology is adding another layer of insight. Observations from missions like the Planck Space Observatory have provided extremely precise measurements of the early universe. These measurements allow scientists to calculate the exact ratio of matter to radiation, to determine how much matter must have survived the annihilation phase. And these numbers are not approximate. They are precise to remarkable accuracy, which means that any successful theory must reproduce them exactly. There is no room for vague explanations, no space for broad approximations. The solution must match the data with precision. This is where theoretical models are beginning to show progress. Some versions of leptogenesis combined with specific neutrino properties are able to produce the correct level of asymmetry. They are not proven, but they are consistent. They align with both particle physics experiments and cosmological observations, and that alignment is significant because it suggests that the answer may not be entirely out of reach. At the same time, researchers are exploring extensions of the standard model that introduce new particles or interactions. These models often predict small deviations in measurable quantities, deviations that can be tested in experiments. And in some cases, early data has shown anomalies, small discrepancies between prediction and observation, not large enough to claim a discovery, but large enough to attract attention. For example, certain decay processes observed at CERN have shown slight deviations from expected behavior. These anomalies are still under investigation. They could turn out to be statistical fluctuations, or they could be the first signs of new physics, and this is the nature of a potential breakthrough. It does not arrive fully formed. It begins as a pattern, a hint, a deviation that refuses to disappear as more data is collected. If these gain patterns persist, they could point toward the existence of new particles or forces, elements of reality that we have not yet incorporated into our models, elements that could provide the missing mechanism for the matter-antimatter imbalance. What makes this moment particularly exciting is the way different fields are converging. Particle physics, neutrino physics, cosmology, all contributing pieces of the same puzzle, all refining their measurements, all pushing toward greater precision. And as they do, the range of possible explanations narrows. Theories that do not match the data are discarded. Those that remain become more refined, more specific, more testable. This process does not guarantee a quick answer, but it does bring clarity. It transforms the problem from an open mystery into a structured investigation, one where each new result moves us closer to understanding. And perhaps the most important realization is this: the imbalance that allowed the universe to exist is not random. It follows patterns. It obeys rules that we are beginning to glimpse, but have not yet fully understood. This is what makes the possibility of a breakthrough feel real, not because we are certain of the answer, but because we are beginning to see the shape of it, the outlines of a mechanism that connects the smallest particles to the largest structures, a mechanism that explains how a tiny asymmetry could grow into an entire universe. And if that mechanism's confirmed, it would represent one of the most significant discoveries in the history of science, because it would answer a question that has lingered since the beginning of time. Why is there something instead of nothing? But even as we approach that possibility, there is still a need to understand it in simpler terms, to translate these complex ideas into something more intuitive, because at its core, this is not just a technical problem, it is a story about imbalance, about how a tiny difference can change everything. And to truly grasp that, we need to step back and look at it from a different perspective, one that makes the scale of the effect easier to understand. To understand how something so small could shape everything, you have to step away from particles and equations for a moment, because the imbalance that created the universe is almost impossible to visualize directly. It is too tiny, too abstract, too far removed from everyday experience. So instead, imagine something simple. Imagine flipping a coin, not once but billions of times. Each flip represents a pair of particles in the early universe. One side is matter, the other is antimatter. Now, if the coin is perfectly fair, you would expect the results to be balanced. Half heads, half tails. And if every head cancels with a tail, you are left with nothing. A perfect balance that eliminates everything. This is what the universe should have looked like. Now imagine something slightly different. The coin is not perfectly fair, is biased, but only by the smallest amount, so small that you would not notice it in a few flips, or even a few thousand. But over billions of flips, the imbalance becomes clear. You begin to accumulate more heads than tails, not by much, but enough that after all the cancellations, some heads remain. That is the universe. Each of those surviving heads represents matter that was not annihilated, matter that went on to form everything, and the bias that caused this outcome is incredibly small. So small that it's almost invisible in individual events, but over the scale of the entire universe it becomes everything. According to calculations based on observations discussed in journals like Nature, the imbalance is roughly one extra matter particle for every billion pairs. That means that for every billion times the coin was flipped, there was only one extra head, one survivor, one particle that did not have a counterpart to destroy it. At first, that might not seem like much, but now imagine scaling that up. The early universe contained an enormous number of particles, far beyond anything we can easily comprehend, and for every billion pairs one survived, that tiny fraction multiplied across the entire universe becomes all the matter we see today. Every atom, every molecule, every structure, all of it originates from that slight bias. This is what makes the problem so fascinating, because it shows how sensitive the universe is to initial conditions. A tiny difference at the beginning can lead to enormous consequences later. This idea appears in many areas of science, in chaos theory, in population dynamics, in the behavior of complex systems. Small changes can amplify over time, leading to vastly different outcomes. But in this case, the scale is cosmic. The difference between existence and nothingness depends on a deviation so small that it is almost indistinguishable from perfect symmetry, and yet it is enough. Now consider what this implies. If the bias had been slightly different, the universe would not look the same. If it were smaller, there might not be enough matter to form galaxies. If it were larger, the universe might have evolved in a completely different way, perhaps collapsing too quickly, or forming structures too dense for life to emerge. What we observe is not just any outcome, it is a very specific one, a result that sits within a narrow range of possibilities. And that raises a deeper question. Why this value? Why this specific level of imbalance? Was it determined by some underlying law, or was it the result of a process that could have turned out differently? Physics does not currently provide a definitive answer, but it does offer ways to explore the possibilities. One approach is to look for patterns, to see whether the imbalance is connected to other properties of the universe. For example, the distribution of matter on large scales, the behavior of fundamental particles, the properties of forces. If these features are related, they might point toward a common origin. Another approach is to test the limits of symmetry, to see how and where it breaks down. Experiments at CERN continue to probe these limits, searching for new forms of asymmetry, looking for deviations from expected behavior, and each new result helps refine our understanding. But even with these efforts, the core idea remains simple. A tiny bias created everything. A slight preference in the laws of physics allowed matter to survive, and that survival shaped the entire universe. This perspective changes how you think about existence, because it suggests that the universe is not just the result of large forces and grand structures. It is also the result of delicate imbalances, subtle differences that are easy to overlook, differences that only become visible when you consider the full scale of time and space. And it invites you to imagine the alternative, a universe where the coin was perfectly fair, where every particle had an exact counterpart, where every interaction ended in annihilation, a universe with no stars, no galaxies, no light, no observers to ask questions, just an expanding sea of energy gradually fading into emptiness. That universe is not hypothetical in the sense of being impossible. It is what our equations would predict under perfect symmetry, which means that the universe you are part of exists because symmetry was not perfect, because the coin was slightly biased, because something somewhere introduced a tiny difference, and that difference changed everything. But this analogy, while helpful, only scratches the surface, because it does not explain why the bias exists. It only shows what the bias does. To understand the origin of that bias, we have to go deeper, back into the earliest moments of the universe, back to the processes that could have created the imbalance. And as we do, we begin to see how this tiny difference connects to the formation of everything around us, from the smallest particles to the largest galaxies. Now imagine that tiny imbalance not as a number, but as a starting condition, a seed, something that exists at the very beginning and quietly shapes everything that follows. Because once even a small excess of matter survives, the story of the universe changes completely. Instead of ending in annihilation, it continues. It evolves. It builds structure, and that process unfolds over billions of years. At first, the surviving matter is not organized. It exists as a hot, dense plasma, a mixture of particles moving at incredible speeds, colliding constantly, interacting through fundamental forces. But as the universe expands, it cools, and as it cools, new possibilities emerge. Particles begin to combine. Quarks form protons and neutrons. Protons and neutrons combine to form simple nuclei, hydrogen, helium, the first building blocks of matter. This process, known as nucleosynthesis, occurred within the first few minutes after the Big Bangs, and it depended entirely on the presence of matter. Without that initial imbalance, there would be no protons to combine, no nuclei to form, no atoms to emerge. Everything that follows begins here. As the universe continues to expand, it cools further, eventually reaching a point where electrons combine to nuclei, forming neutral atoms. This moment is known as recombination, and it marks a transition from a universe filled with charged particles to one where light can travel freely. The radiation released at this time is still observable today as the cosmic microwave background. Measured in detail by missions like the Planck Space Observatory, this radiation carries information about the early universe, about the distribution of matter, about the tiny fluctuations that would later grow into galaxies. But again, none of this would exist without the initial imbalance. Without matter, there would be no atoms to interact with light, no structures to form, no facio. Amplify. After recombination, gravity begins to take over. Small differences in density, regions where matter is slightly more concentrated than average, start to attract more matter. These regions grow over time, slowly at first, then more rapidly, eventually collapsing into the first stars and galaxies. According to observations from the Hubble Space Telescope and the James Webb Space Telescope, some of these structures form surprisingly early, Within a few 100 million years after the Big Bang, this suggests that the initial conditions were just right, that the imbalance not only allowed matter to exist, but allowed it to organize efficiently. Stars begin to form, and with them new processes emerge. Inside stars, nuclear fusion creates heavier elements: carbon, oxygen, iron, elements that did not exist in the early universe. These elements are later dispersed through supernova explosions, seeding space with the moed needed for planets and life. All of this traces back to that original asymmetry, because without it there would be no stars, no fusion, no elements beyond hydrogen and helium. The universe would remain simple, static, empty of complexity. But with even a tiny excess of matter, complexity becomes possible, and complexity leads to structure. Structure leads to diversity, and diversity leads to the conditions necessary for life. This is where the story becomes deeply interconnected, because the same imbalance that allowed galaxies to form also allowed you to exist. Every atom in your body is part of that chain. A direct consequence of the survival of matter in the earliest moments of the universe. This connection is not abstract. It is physical, real, measurable. The carbon in your cells was forged in stars, stars that formed from clouds of matter, matter that survived annihilation. Because of a tiny asymmetry, this perspective shifts the scale of the problem. It's no longer just about particles, it is about everything. The entire cosmic history is built on that initial difference, and this is what makes the mystery so profound, because it is not just about explaining a detail, it is about explaining the foundation of reality, why there is something rather than nothing, why the universe has structure instead of emptiness, why complexity emerged instead of simplicity. And as scientists study the large-scale structure of the universe, they see patterns that reflect this origin. Galaxies arranged in vast filaments, clusters connected across enormous distances, voids where matter is sparse. These structures are not random. They follow from the initial conditions, from the distribution of matter after the early universe cooled, and those conditions in turn depend on the existence of matter itself. Without the imbalance, none of these patterns would exist. The universe would be uniform, featureless, a smooth distribution of energy with no structure to observe. This is why the problem of matter-antimatter asymmetry is so central. It's not just one question among many. It's a key that unlocks multiple aspects of cosmology, particle physics, astrophysics, even the study of life. Because all of these fields depend on the existence of matter. And the existence of matter depends on a process we do not yet fully understand. As we trace this chain from particles to galaxies to life, we begin to see how interconnected everything is, how a tiny difference can propagate through time, how it can influence events billions of years later, how it can shape the universe at every level. And this realization leads to an important shift. Because instead of asking how the imbalance created the universe, we begin to ask what it tells us about the laws that govern it, what it reveals about the underlying principles of reality. Because if such a small asymmetry can have such large consequences, then the laws that allowed it must be carefully structured, carefully balanced, and perhaps more complex than we currently understand. Which brings us to the next stage of the story, the implications of this imbalance, not just for the origin of the universe, but for the way we think about physics itself. Once you accept that a tiny imbalance shaped everything, the implications begin to spread outward, not just across the universe, but into the foundations of physics itself. Because if the laws of nature allowed such a precise deviation from symmetry, then those laws may not be as simple or as complete as we once believed. For decades, physics has been guided by the idea that symmetry is fundamental, that the universe at its core is governed by balanced rules that treat opposites equally. This idea has led to some of the most successful theories ever developed. From electromagnetism to quantum field theory, symmetry has been a reliable guide, a principle that helps predict new phenomena and explain observed behavior. But the matter-antimatter imbalance challenges that assumption, not by eliminating symmetry entirely, but by showing that it can be broken, and not just broken in a random way, but broken in a very specific and consistent way. This suggests that symmetry may not be the final rule. It may be part of a deeper framework, a framework where symmetry exists but can be violated under certain conditions, and those violations may be just as important as the symmetries themselves. In fact, some physicists now view broken symmetry as a driving force in the universe, a mechanism that allows complexity to emerge. Without it, everything would remain uniform, unchanging. Without structure, this idea appears in many areas of physics. For example, the separation of forces in the early universe. At extremely high energies, the fundamental forces may have been unified, but as the universe cooled, these forces separated, each taking on its own distinct properties. This process, known as symmetry breaking, is believed to be responsible for the diversity of interactions we observe today, and it may also be connected to the matter-antimatter imbalance, because the same conditions that allowed forces to differentiate could have created opportunities for asymmetry to develop, opportunities for small differences to be amplified, for preferences to emerge, and once those preferences exist, they can influence everything that follows. This leads to a broader implication, that the universe may not be perfectly neutral. It may have built-in tendencies, subtle biases that shape its evolution, not in a way that is obvious at first glance, but in ways that become significant over time. This challenges the idea of a perfectly balanced universe, and replaces it with something more dynamic, a system where balance exists but is not absolute, where symmetry is present but not unbreakable, and where small deviations can lead to large consequences. Another implication concerns the completeness of our current theories. The Standard Model, as successful as it is, cannot fully explain the matter-antimatter imbalance, which means that it is not the final description of reality. There must be additional physics, new particles, new interactions, or new principles that extend beyond what we currently know. This is not unusual in science. Many theories have been expanded or replaced as new data becomes available. But in this case, the stakes are particularly high because the missing piece is not a minor detail. It is something that affects the existence of everything. And so the search for new physics is not just about curiosity, it is about necessity. Experiments at CERN and other facilities are designed not only to test existing theories, but to look for signs of what lies beyond them. Deviations from expected behavior, unexpected results, anomalies that cannot be explained within the current framework. These are the clues that could lead to a deeper understanding. At the same time, cosmology provides another perspective. By studying the large-scale structure of the universe, scientists can infer the conditions that existed at its beginning. Observations from the Planck Space Observatory and other missions reveal patterns that must be explained by any complete theory. Patterns that reflect the distribution of matter, the behavior of energy, and the evolution of the universe over time. These observations act as constraints. They limit the range of possible explanations. They guide the development of new models, and they ensure that any proposed solution must match reality. This interplay between theory and observation is essential, because it prevents speculation from drifting too far from evidence. It grounds ideas in data, and it allows progress to be measured. But even with this careful approach, the implications of the imbalance continue to expand. They reach into questions about the origin of the universe itself, because if symmetry was broken in a specific way, then the initial conditions of the universe may have been more complex than we assume. Perhaps the Big Bang was not a perfectly symmetric event. Perhaps it contained inherent fluctuations, or processes that favored certain outcomes. These possibilities are still being explored, and they are difficult to test, but they highlight how the problem extends beyond particle physics, into cosmology, into the study of the universe as a whole. There are also philosophical implications, not in the sense of abstract speculation, but in the sense of how we understand existence, because the realization that everything depends on a tiny imbalance changes perspective. It suggests that the universe is not inevitable. It could have been different. It could have been empty. And the fact that it is not raises questions about probability, about necessity, about the nature of physical laws. Are they fixed? Or could they have been different? Do they determine outcomes strictly, or do they allow for variation? These are not questions with easy answers, but they are part of the broader context of the problem. and they show how a scientific mystery can connect to deeper ideas about reality. As we continue to explore these implications, one thing becomes clear. The matter-antimatter imbalance is not an isolated issue. It is a window into something larger, something that touches multiple areas of science, something that may lead to new discoveries, new theories, new ways of understanding the universe. But despite all the progress, there is still a significant gap, a set of questions that remain unanswered, questions that define the limits of our current knowledge. And as we move forward, those unanswered questions become the focus, because understanding what we do not know is just as important as understanding what we do. It is what drives the search for answers, and it is what keeps the mystery alive. Even after decades of research, the most important question remains unanswered. What actually caused the imbalance? Not in general terms, not as a broad idea, but as a specific testable mechanism that can explain exactly how matter came to dominate. Because while we have frameworks, conditions, and theories, we still lack a definitive answer. And that absence is not due to a lack of effort. It's due to the difficulty of the problem itself. The events that created the imbalance occurred in the earliest moments of the universe, at energies far beyond what we can currently reproduce, under conditions that no longer exist. We are trying to reconstruct a process that happened billions of years ago, using fragments of evidence that have survived to the present, and while those fragments are incredibly informative, they're not complete. One of the biggest unknowns is the exact nature of CP violation in different sectors of physics. We have observed it in certain particles, but we do not know whether it behaves the same way in all systems, or whether there are additional sources that we have not yet detected. For example, neutrinos remain one of the most promising areas of investigation. Experiments connected to Fermilab and KEK are still working to determine whether neutrinos and antineutrinos behave differently. If they do, it could provide a major piece of the puzzle, but the measurements are extremely challenging. Neutrinos interact so weakly that detecting them requires massive detectors and long observation times. Even then, the signals are subtle, difficult to interpret, and subject to uncertainty. Another unknown involves the possibility of new particles. Many theories that attempt to explain the imbalance rely on particles that have not yet been observed. These particles may have existed only in the early universe, decaying rapidly and leaving behind an asymmetry, or they may still exist but interact so weakly that we have not detected them. Experiments at CERN and other facilities are searching for signs of these particles, looking for deviations from expected behavior, looking for hints that something new is present, but so far no conclusive evidence has been found. There are also questions about the role of phase transitions in the early universe. If the universe underwent rapid changes in its fundamental properties, these transitions could have created conditions where symmetry was broken. But the exact nature of these transitions is still uncertain. Were they smooth, or were they abrupt? Did they occur uniformly across space? Or did they create localized regions with different properties? These details matter because they determine how asymmetry could have developed and spread. Cosmological observations provide some constraints. Data from the Planck Space Observatory gives us a snapshot of the universe diverse at a very early stage. But even this snapshot comes from a time after the imbalance was already established. It shows us the result, not the process, which means that we still have to infer the cause. Another major uncertainty is whether the imbalance is connected to other mysteries in physics, such as dark matter. If the processes that created dark matter are linked to those that created the matter-antimatter asymmetry, then solving one problem could help solve the other. But this connection is not yet confirmed. It remains a possibility, one among many. There is also the question of whether our current theoretical framework is sufficient. The Standard Model, while incredibly successful, does not include gravity in a unified way. It does not explain dark matter, and it does not account for the matter-antimatter imbalance. This suggests that it is part of a larger theory, one that we have not yet fully developed. And until we have that larger theory, our understanding will remain incomplete. What makes this situation particularly challenging is that many of these unknowns are interconnected. Solving one may depend on solving another. Understanding CP violation in neutrinos may require new physics. Discovering new particles may depend on reaching higher energies. Interpreting cosmological data may require more precise measurements. Each piece of the puzzle is linked to others, and progress in one area often depends on progress in another. This creates a complex landscape. A network of questions rather than a single problem, and navigating that landscape requires careful coordination between theory and experiment, between observation and interpretation. Despite these challenges, there is a sense of progress, not in the form of a final answer, but in the narrowing of possibilities. Theories that do not match observations are ruled out. Those that remain become more refined, more specific, more testable. This process is slow, but it is effective. It ensures that when an answer is found, it will be grounded in evidence, not speculation. And perhaps the most important realization is this: we now know what we are looking for. We understand the conditions that must be satisfied. We have identified the key areas where new physics may be found, and we have the tools to investigate them. What we lack is the final piece, the mechanism that connects all the evidence into a coherent explanation, and until that mechanism is discovered, the mystery remains open. A reminder that even in a universe filled with knowledge, there are still fundamental questions waiting to be answered. Questions that challenge our understanding. Questions that push us to explore further. Questions that define the frontier of science. And as we look ahead, the focus shifts toward the future. Toward the experiments and observations that may finally provide the missing answers. Toward the technologies that will allow us to probe deeper into the nature of reality. And toward the possibility that the solution is closer than we think. To solve a mystery that began at the birth of the universe, scientists are building tools that push the limits of what is physically possible. Not just larger machines, but more precise ones, more sensitive, more capable of detecting the faintest signals hidden within overwhelming noise. Because the answer to why the universe exists may not be dramatic, it may be subtle. A tiny deviation, a slight preference, something that only becomes visible when measurements reach extraordinary levels of accuracy. One of the most important efforts is the next generation of particle physics experiments. At CERN, upgrades to the Large Hadron Collider are already underway. The High Luminosity Large Hadron Collider will allow scientists to collect far more data than before, increasing the chances of detecting rare processes that could reveal new sources of asymmetry. With more collisions, researchers can study particle decays in greater detail, measure CP violation with higher precision, and search for signs of new particles that may have influenced the early universe. But particle accelerators are only one part of the story. Neutrino experiments are entering a new era. Projects like the Deep Underground Neutrino experiment supported by Fermilab aim to measure neutrino behavior with unprecedented accuracy. By sending beams of neutrinos across vast distances and observing how they change, scientists hope to determine whether neutrinos violate symmetry in a way that could explain the matter-antimatter imbalance. If strong CP violation is confirmed in neutrinos, it would be a major breakthrough, providing direct support for theories like leptogenesis, and bringing us closer to understanding the origin of matter. At the same time, experiments in Japan at KEK continue to refine their measurements, using advanced detectors to track neutrino interactions with greater precision. These efforts are complementary, different approaches to the same question, each adding to the overall picture. Beyond particle physics, astrophysical observations are also advancing. The James Webb Space Telescope is providing detailed views of the early universe, observing galaxies that formed shortly after the Big Bang, studying how matter organized itself in those early stages, and offering clues about the initial conditions that must have existed. These observations do not directly reveal the mechanism of asymmetry, but they provide constraints. They show what the universe looked like at different times, and any successful theory must be consistent with these observations. Future missions are planned to go even further. New telescopes designed to map the distribution of matter across vast distances, to study the cosmic microwave background with even greater precision than the Planck Space Observatory, and to search for subtle signatures that could point to new physics. There are also experiments focused on detecting rare processes, such as proton decay. If protons are not perfectly stable, their decay could provide evidence for theories that unify the fundamental forces, theories that may also explain the matter-antimatter imbalance. Facilities around the world are searching for these events, watching enormous volumes of material for the faint signals of a single decay, because even one confirmed observation could reshape our understanding of physics. Another frontier involves the search for electric dipole moments in particles. If certain particles have a slight asymmetry in their charge distribution, it would indicate new sources of CP violation. Experiments designed to detect these moments are becoming increasingly sensitive, pushing the limits of measurement, looking for effects that are incredibly small but potentially very significant. All of these efforts share a common goal: to uncover the mechanisms that broke symmetry in the early universe, to identify the process that allowed matter to survive, to move from possibility to certainty. What makes this moment unique is the combination of technologies available: particle accelerators, neutrino detectors, space telescopes, each providing a different perspective, each contributing a piece of the puzzle, and together they create a powerful system for exploring one of the deepest questions in science. But there is also a recognition that the answer may not come quickly. It may require years, decades, perhaps even new technologies that have not yet been developed, because the scale of the problem is immense, and the signals we are searching for are subtle, hidden within complex data, difficult to isolate, difficult to interpret, and yet there is reason for optimism, because progress is measurable. Each new experiment refines our understanding. Each new observation narrows the possibilities. Each new result brings us closer to the truth. And perhaps the most important aspect of this search is that it's not limited to a single field. It is a collaboration across disciplines, across countries, across generations of scientists, all working toward the same goal: to understand why the universe exists, to uncover the origin of the imbalance that made everything possible. And as these efforts continue, the boundary between what we know and what we do not know begins to shift. What was once mysterious becomes understood. What was once impossible becomes testable. And the question that seemed beyond reach begins to feel within grasp. But even as we approach that possibility, there is one final step in this journey, a step that moves beyond data and theory and into reflection, because understanding how the universe exists is one thing. Understanding what that means is another. If the universe should not exist and yet it does, what does that really mean? Not as an equation, not as a data set, but as a realization. Because everything you have just followed, every experiment, every theory, every observation points toward a single quiet conclusion. Existence itself depends on a fragile imbalance, a difference so small that it almost disappears inside the laws that created it. And yet without that difference, nothing would remain. No light, no structure, no time as we experience it. Just energy spreading outward, never forming anything at all. When scientists say that the universe should not exist, they are not making a dramatic statement. They are describing a logical consequence. If symmetry had been perfect, annihilation would have been complete, and reality as we know it would never have taken shape. But symmetry was not perfect. Something shifted, something allowed a tiny excess of matter to survive, and from that survival, everything else followed. This changes how you see the universe, because it is no longer just a vast collection of objects. It is the result of a very specific condition, a condition that could have been different, a condition that might not have existed at all, and that realization introduces a sense of contingency, the idea that the universe is not inevitable, that it could have unfolded in another way, or perhaps not unfolded at all. In physics, we often look for necessity, for laws that determine outcomes with certainty, but the matter-antimatter imbalance suggests something more subtle, that the laws allow for possibilities, that within those possibilities certain outcomes emerge, and those outcomes shape everything that follows. This does not mean the universe is random. The processes that created the imbalance were governed by physical laws. They followed rules, they produced consistent results, but within those rules there was room for deviation, room for a tiny preference to develop, and that preference made all the difference. It is easy to think of this as a technical detail, a small correction in an otherwise complete theory, but it is more than that. It's a reminder that even the most fundamental aspects of reality can depend on delicate conditions. Conditions that are not obvious at first glance. Conditions that only reveal themselves through careful study. And when you step back, you begin to see how everything connects. The imbalance between matter and antimatter, the formation of atoms, the birth of stars, the creation of elements, the emergence of planets, the development of life. All of it traces back to that initial moment, that slight deviation from perfect symmetry. And that connection is not abstract, it is direct. Every atom in your body exists because matter survived, because somewhere in the earliest moments of the universe the balance tipped just enough Not too much, not too little, just enough to allow structure to form, just enough to allow complexity to emerge, just enough to allow you to exist and ask this question. Why? Why did the balance tip in that way? Why not to another? Why not none at all? These are questions that science is still trying to answer, and they may take time, because they reach into the deepest layers of reality, layers that we are only beginning to explore. But even without a final answer, the journey itself reveals something important. It shows that the universe is not as simple as it first appears, that beneath the vastness and the order there are subtle effects, hidden mechanisms, processes that operate on scales we can barely detect, and yet those processes determine everything. This perspective does not diminish the universe, it deepens it. It adds complexity, it adds nuance. It shows that existence is not just about large forces and grand structures. It is also about small differences, tiny imbalances that ripple outward through time and shape the entire cosmos. There is also a sense of scale in this realization, because when you consider how small the imbalance is and how large the universe has become, the contrast is striking. From one extra particle in a billion to trillions of galaxies spread across unimaginable distances, from a tiny deviation to everything. This is the power of cumulative effects, of processes that build over time, of small beginnings leading to vast outcomes, and it invites a different way of thinking about the universe, not as something fixed and inevitable, but as something that emerged from a set of conditions that could in principle have been different, and yet are exactly what they are. This does not imply purpose or design. It reflects the outcome of physical processes that we are still trying to understand, processes that may reveal new principles, new laws, new insights into the nature of reality. As future experiments continue, as new data is collected, as theories are refined, we may eventually uncover the mechanism that created the imbalance. We may understand how symmetry was broken, and why it was broken in exactly the way required for the universe to exist. But even then, there may be deeper questions about why those laws exist, why those conditions were possible, why reality takes the form it does. And those questions may lead us further, beyond the current boundaries of physics, into new areas of exploration, new ways of thinking, new frameworks for understanding the universe. For now, what we know is this: the universe should not exist in the way we observe it, and yet it does. And that fact is not just a mystery. It is a clue that there is more to discover, more to understand, more to uncover about the nature of existence itself. And as you look out into the night sky, at the stars, the galaxies, the vast expanse of space, you're not just seeing distant objects, you're seeing the result of a tiny imbalance, a subtle difference that made everything possible, a difference that should not have been there, and yet somehow is